In this video, I derived the formula for the distance between a point and a line. This is the example that we're going to do. And then once we know the distance between a point and a line, we can use that, to infer the distance between two parallel lines. Okay, so let's figure out how to find this distance between some line and point Q not on the line. Well, if I have the parametric equations of the line, by plugging in a t-value, any t-value, we can get a point P on the line. And there's no guarantee of where that P is located. P could be there, or P could be there. That'd be nice. We'd find the distance between Q and P like that. P could be over here. P could be way down here. But we plug in a value of t, and then we're going to be able to infer a single point on the line. Also, if we have the parametric equations of the line, the coefficients of t, like the 2 in this case, and the 1 in this case, and the 2 over here, those are the direction numbers, the components of the direction vector of our line. So V has components A, B, C, and it goes that way. Or if we prefer, we could draw it right on here. There's the vector V. It has components A, B, C, and it's on the line. Now when we talk about the distance between the point Q not on the line and the line, we're talking about the shortest distance. Just like the distance between a point and a plane, there's lots of distances between that point Q and the line. I could take the distance from there to there, distance from there to there, distance from there to there, and then there, and then the shortest one is at a right angle with the line. And then if I go over here, the distances from those points on the line and Q starts to get longer again. Ideally, we would just identify this point P and find the distance from P to Q. But since we can't do that, we'll just identify some other point P on the line by just plugging in a t-value over here into our parametric equations. Then we'll have a location, an x, a y, and a z that will be the coordinates of our point P. And now we need to use all of this to find a formula for this distance. How can we do that with everything that we know so far? How can we find that distance from there to there? Well, we know vectors. We have studied vectors a lot. So anytime I see a couple of points, or a point over here and a point over there, I'm thinking I should probably make a vector from P to Q. And that's a good idea, because now our vector PQ and our vector V, at least the way I've drawn them here, have the same initial point. They're drawn tail to tail, so the angle between them is theta. I always call that angle between the two vectors when they're drawn tail to tail theta. We're saying, well, what's the length of this side of the triangle? Well, that's opposite theta, so that distance, I'm going to call it D, is PQ, or the length of the vector PQ, times the sine of theta, because D is opposite theta in our triangle. And theta is always going to be between 0 and 180, and sine is always positive between 0 and 180 degrees, or 0 and pi radians. So this would be our distance, and that's if we know the angle theta, but most of the time we don't. We have the coordinates of P, the coordinates of Q, and we can usually look at the components, or we can look at the components of this vector, or alternatively, we can look at the parametric equations of the line to infer the components of V. So we've got V and we can find PQ, but we don't know theta. So we're going to multiply, just like we did before. We say, hey, that looks a lot like a cross product, or the length of a cross product. So I'm going to multiply by the length of V, length of the direction vector, and divide by the length of V. And what do you know? That is the magnitude of the cross product of PQ with V. Oops. divided by the length of v. So that's our formula. We need to find PQ, we need to find V, we need to take its cross product, we need to find its length, and then we need to divide by the length of V. So I'm going to outline those steps for you right here. Notice we're given Q and we're given R. So the first thing I need to do is identify x of t, y of t, and z of t. So this is x, this is my y of t, and this is z of t. Those are the components in my vector equation of the line. The line that we're interested in. Okay, and now in order to find a point P on the line, I can substitute any t value I want into this, and the terminal point of that vector, and when it starts at the origin, that is going to be our location. So the first thing we do is we find a point P on the line, by substituting a value of t into r of t. So I'm just going to choose the easiest one, t equals 0. So if r of 0 is 2 times 0 times I hat plus 0 minus 3 times j hat plus 2 times 0 plus 2 times k hat. So we just get 0, negative 3, 2. Now that's a vector. The point P has this location. That's the x, the y, and the z when t equals 0. So we have that. We also need to identify the direction vector of the line. So we're trying to find A, B, C, and remember A, B, and C are the coefficients of t in our parametric equations of the line. A is the coefficient of t on the x component. So A is 2. B is the coefficient of t on the y component. That's an implied 1 right there. And C is the coefficient of t on the z component, which is 2. So we're here. That's our V. You write that down for your notes. A is the coefficient of t on the x component, or the parametric equation for x. This is the x component of r of t. B is the coefficient of t on the y component, and C is the coefficient of t on the z component. Okay, alright, so we've identified V, we have P, we were given Q, now I just need to find PQ, cross it with V, find the length, and divide by the length of V. Okay, so first we'll find PQ. The vector from P to Q looks like this. Start with the coordinates of Q. Q is at this location, 1, negative 2, 4. So x, y, and z, remember, those are locations. Now we're subtracting the coordinates of P. So we're subtracting a 0, a negative 3, and a 2. Now, if you chose a different value of t, I chose t equals 0 and I got this p. If you choose t equals 1, you're going to get a different p. The math is still going to work out just fine. Any p you choose on that line, this is going to work. For this p, we've got coordinates 0, negative 3, and 2. So we subtract those. We get 1. We're subtracting a negative 3, so that's adding 3, so that's 1. And then that component is 2. So I've got PQ. Now I need to do PQ crossed with V. take the cross product. I'm just going to use that determinant form. I hat, j hat, and k hat in the first row. PQ's components go here, and the components of V go here. Okay. Cross out the row and column containing I hat. Multiply across, and subtract. So we get 2 minus 2, so 0. Then you have a negative. It's always negative for that second component. Sign alternates. Cross out the row and column containing j hat. You have 1, 2, and 2, 2. So you're going to do 1 times 2 is 2, minus 2 times 2, which is 4. And then we cross out the row and column containing k hat. You have 1 minus 2. There. So we have 0. That's a negative, negative 2, which is 2, and a negative 1. So that is PQ cross V. I need the length of that, and I need to divide it by the length of V. So we're going to compute the length of this vector. There's a bit of an order of operations. You've got to find PQ, then you've got to cross it with V, then you've got to find the length. So when you see this, sort of think through what steps would you have to do to evaluate this. This might look like a mess to you, but hopefully if I ask you to find PQ, you can do that. If I ask you to take a cross product, you can do that. And then if I ask you to find the length of a vector, you can do that. So this isn't nearly as bad as it seems. So I've got PQ crossed with V. I want the length. Take the components, square them, add them, and take the square root. 4 plus 1 is 5, so we get square root of 5. Now the other thing I need for my formula is the length of V. So the length of that direction vector, and then we're going to divide and we'll be done. V had components 2, 1, 2, so its length is the square root of 2 squared plus 1 squared plus 2 squared. 4 plus 4 is 8. 8 plus 1 is 9. Square root of 9 is 3. And that means the distance equals, so we're substituting into your formula, but the cross product of PQ and V, its length divided by the length of V, so we get square root of 5 over 3. Alright, that's a lot of steps. But remember, you're going to have this formula on your sheet. I highly recommend having this formula on your sheet and a picture like this on your sheet to remind you. I'm going to give you Q, and I'm going to either give you the parametric equations of the line or the vector equation of the line. With the vector equation of the line, you identify the x, the y, and the z, and then you go on from here. First, you need a point P on the line, so substitute a value of t to get a point P. Identify V by reading off the coefficients of t in your x, your y, and your z. Find the vector from P to Q. You found P, you were given Q, so you find this. Now you've got V and PQ, so you want to take the cross product. After you've taken the cross product, find its length. Find the length of the direction vector, and then you just divide those two guys. The length of the cross product divided by the length of the direction vector. Now, if I ask you for distance, I do not want to see a vector. Distance is a scalar. So this should be a number. If you find that you have a vector divided by 3, something went wrong, and chances are you just forgot to take the length of the cross product in the numerator. Okay, so that's the shortest distance between a point and a line. Let's say you want to find the distance between two lines. Now, if I have two lines and they're not parallel, if this is line 1 and this is line 2, well, the shortest distance between the two lines is 0 because they cross somewhere. It's also possible that you might have this line 2 and then line 1 crosses like this, but in a parallel plane. And you want the shortest distance between those two lines. So it might look like this, but like maybe this one is much closer to us than line 2 is. I don't know how to draw that so that it's closer. Or if you might have two lines in space that are parallel to each other, just like lines in the plane. They never cross. And there is one shortest distance between the lines. It's that distance, that perpendicular distance between the two parallel lines. So let's see what we've got here. Let's see if we've got parallel lines so that we can find this distance between them. The shortest distance between them. I know we could find a distance from there to there, but that's not the shortest. Anytime somebody asks you, or often when somebody asks you for distance in this class, especially in geometry, they're talking about the shortest distance between those two objects. Okay, so let's look at this one. Our first line has these parametric equations. This is x of t, this is y of t, and this is z of t. And the direction vector of this line comes from reading off the coefficients of t. So I've got a -1 multiplying my t for the x. So that's my x component. And a 2 multiplying the t for the y. And a 1 multiplying the t for the z. So that's the direction vector there. And here I've got x of t, y of t, and z of t. Let's find its direction vector. So I'll call that v1 for the first one. Direction vector of line 2 is v2. Its direction vector has components. Well, the x component is the coefficient of t on the x component of r here. So we have a 3. And then the y component is the coefficient of t there, so -6. And then the coefficient of t there, that's a -3. Question, are those two parallel to each other? If I multiply that by a constant, can I get this one? I sure can. -1 times -3 would give me that 3. So let's try multiplying v1 by -3. So I've got -3 times the vector -1, 2, 1. Distribute your scalar. You multiply each of the components by your scalar. And I get 3, -6, -3. Hey, that's v2. So what does that mean? Here's v1. And v2 is -3 times that. So it's 3 times as long in the opposite direction. So those are parallel to each other. V1 is parallel to V2. Now, it might be the case that these are exactly the same line. In that case, the distance between the two lines would be 0. But let's suppose they're not. Even so, if we tried to find the shortest distance between the two lines using this formula, well, we'll see in a second, and I'll come back to that point in just a second. Okay, so V1 and V2 are parallel, so that means either I've got parallel lines that don't overlap, or they're exactly the same line. If they're exactly the same line, obviously the distance between the two lines is 0. It turns out that formula will give us a 0 if they're exactly the same line. If they're not exactly the same line, our formula will give us this distance from here to here. Now, in order to do that, I'm going to draw another picture that doesn't have so many little little marks on it. So let's call this line 1 and this one line 2. Alright, this is the vector v, and negative 3v is that way, so they're parallel to each other. Now if I want the shortest distance between the two lines, I'm basically going to find the distance between one line and a point on the second line, using the same formulas that we did on the previous page. So what I need is a point Q on line 2, a point P on line 1, then I'll find the vector from P to Q, and then I'll find like that side, that missing side of the triangle. If this is the angle theta, the distance between the two lines is going to be the length of the hypotenuse, which is the length of PQ, times the sine of theta, and we know to multiply by the length of V over the length of V. And this is the magnitude of the cross product of those two guys. And that is the length of V in the denominator. So that's going to give us this right here. But in order to do that, I need to find a point Q on one line and a point P on the other line. Okay, so this is the first thing we did was the very first thing we did was we found the direction vectors of both lines. Then we showed that the direction vectors are parallel. Given that the direction vectors are parallel, the distance between the two lines can be found using this formula. Okay. So the third thing I want to do after finding the direction vectors, showing that the vectors are parallel, is find a point Q on the second line. So you can plug in any t value you want over here, and that's going to give you the position. This is what we call a position vector in the next chapter. It's going to give you the position of some object at that time. So I'm going to substitute t equals 0 into R2, calling that R sub 2 for line 2. And we get 3 times 0 times I hat plus the quantity 1 minus 6 times 0 times j hat plus the quantity 4 minus 3 times 0 times k hat. And this is 0, 1, 4. And so the point Q is at this location. That's a vector. Don't say that Q is that vector, because Q is not a vector, Q is a point. Q is the point 0, 1, 4. Now we need to do the same thing on line 1. Just for ease, I'm going to substitute in t equals 0 again. Got 2 minus 0. I'm substituting into this right here. 2 minus 0, 3 plus 2 times 0, and 4 plus 0. So I have 3 plus 2 times 0 and 4 plus 0. And we work this out, and we get that. And so that is the location of P. Now, in order to use this formula, I need to compute PQ. I need to take one of the direction vectors V, the direction vector V for line 1, and cross it with PQ. I'm going to put a V1 there because we're using line 1. And then we're going to divide by the length of the direction vector for line 1. Okay, so one piece at a time. Let's find PQ. So we use the coordinates of the terminal point, subtract the coordinates of the initial point. So we get -2, -2, 0. Now we want to find the cross product of PQ and V1. So I'm going to use my determinant form. V1 has components -1, 2, +1. Let me cross out the row and column containing I hat. Multiply, so that's -2. Multiply, that's 0, and subtract, minus for the y component. Cross out the row and column containing j hat. We're going to have -2, -0. And then lastly, we cross out the row and column containing k hat. We're going to have -4, minus a 2. That's negative times a negative is a +2, and we're subtracting that +2. And so PQ crossed with the direction vector of the first line is this. It's a -2 is a +2. Okay, what do I need to do next? I need to find the length of that vector, and I need to divide by the length of V1. So we're just going to find a couple of lengths. Take the components, square them, add them, and take the square root. So I have 4 + 4 + 36, so that's going to be 44. For V was way back here. That was our V, -1, 2, 1. So take the components. We're going to square them, add them, and take the square root. 1 + 1 is 2, + 4 is 6. And then the last thing we do is we find the distance. Distance equals the length of PQ crossed with V1 divided by the length of V1. And so we get square root of 44 divided by square root of 6. We could stop there, or if you prefer to rationalize, you're welcome to. Let's see, 44 times 6. If we take the square root of that, we get 2 root 66, all divided by 6. And 2 goes into 6 3 times, so we get square root of 66 over 3. Either one of these answers is fine for the quiz. Okay, so big picture. If you're finding the distance, the shortest distance between two lines, you need to find a point on one line, a point on the other line, and the direction vector of that first line. I like to use this picture here. It helps me. This picture reminds me, okay, if I'm given my lines in component or in the vector equations of the lines like this, or if I'm given the parametric equations of the line, then I can use those parametric equations to infer V. I can plug in a t value to find Q on one line, and then I can plug in a t value on the other line to find P. Once you've got a P and a Q, compute the vector from P to Q, cross that vector with the direction vector of the first line. So we want this one, not the V2. If you use V2, you're going to be wrong. It has to be the first line. Cross that with the direction vector of the first line, you're going to get this number. Find the length of that cross product, divide by the length of that vector, and you'll get this answer. Okay. So that's it for distance between a point and a line, and the distance between two lines. Notice this is another application of the cross product, and the distance between a point and a plane was another application of the dot product. So we mentioned those previously, and here's where we introduce those applications.